So this course is about sensors and actuators in servo systems. We are going to cover first sensors. The second section will be interfacing, because there's a lot of know-how how to interface sensors to control systems. And the third section of the course is actuators. And we'll start the course with some historical introduction. So today we'll talk for maybe half the time about the history of servo systems, and then we'll get into the actual technical stuff. So what was the first known servo system in the world? You should know that from reading. Who was the first servo engineer in the world? Who is the first person who made a servo system? You should know that. Okay, James Watt. Because James Watt built the first successful steam engine, not the first steam engine, but the first successful steam engine, but he needed a way to control the speed of the steam engine. Before that, there was people who were just standing near the steam engine and turning the steam valve on off, but James Watt wanted a reliable automatic way to control the speed of the steam engine. Why was that important? Why was it important to control the speed of the steam engine? A bit, what is? Pardon?
Control the flow of the steam.
Yeah, but why it was so important? Because why did they care if the steam engine runs slow or fast? What were the first steam engines used for? Well, they were used for two things: to pump waters for mines, but that's the speed didn't matter. But they were used for the elevators to bring the miners up and down. So you really have a lot of incentive to control the speed of the elevators, right? So and that was the incentive to find a way to control the speed of the steam engine. So what I'll do is I'll show you here first, I'll show you here some quick simulation to explain how it works. I just have to find it here. Okay, so I'll show you a couple of very quick videos. And the year of that was 1788. So let me just show you a couple of quick videos. Do it full screen. So this is just a simulation showing you what a governor is. Maybe I'll turn off the lights in the front part. You'll see it better. So as the steam engine speeds up, these two weights lift by centrifugal force. And as they lift by centrifugal force, they turn the valve to shut off the steam. Okay? So if you set the weights or set the spring, if the engine goes too fast, the weights will open up and shut off the steam and regulate the speed. Okay? So let's go escape. Let me just show you a couple of other very quick 1-minute videos about that, and then we'll continue. So I'll show you the actual picture, what it looked like. This is for the picture of Watt's original engine, 1788. These are the two weights, okay? And you can see the chain on top. The chain on top was coupling it to the engine. This is the cogwheel of the big engine at the end. So the chain on top was just like a belt driving the thing. And the lever below the chain, there is a lever. And that lever below the chain was connected to the steam valve. Okay, so that's this, and I'll just show you one more video of a little steam engine running with this governor. Let me just find it. Like HP. Okay. I have a hard time finding it here. So this is just a little engine and somebody explaining how the governor works.
Okay, this video is all about the governor.
That's a model steam engine. You can see it opens up. Now when you start slowing down the engine, it will drop and allow more steam.
I'm just going to throw a load on here.
Okay, so now the governor drops because of speed drops, but as it drops, it opens the steam valve and more steam comes in. Okay? Good. You can stop that. Okay, and Now, so right after that, people became aware that you can do something called a servo, that you can use some set point to control a big thing called a plant. So you know servos maybe from electronics, but servos exist in hydraulics, in steam, in many things, not just electronics, and all they have in common the same thing. There is something we call a plant, even if it's just an op-amp, it's referred to as a plant. This is the output, let's call it V out. Now from the output you have a feedback. Okay, let's say the plant has a gain A. Okay, if it's an amplifier, it's clear, it's just gain, and the feedback is B. Now what you do with the input, you compare the feedback to a reference or to an input. So this is V in, also called sometimes the reference or the input. And what we want the output to track the input, and it senses the output to the feedback. The feedback is negative, and I'm assuming all of you took some courses so this is just very brief introduction. So from this you can write the equation, because the output is simply the input times the gain. So V out is simply the input here times the gain. Gain is A, and the input here is simply V in. Okay, so it's V in minus the feedback. If this is V out, at this point it will be B times V out, because it's multiplied by B. So this is V in, this is B V out. The difference is B V out, okay, B V out minus V in times A, okay, and that difference is multiplied by A to give you V out. So you can rearrange the terms here, so you get V out 1 minus BA. Now of course I can reverse the sign. So here if I rearrange it, I'll get V out 1 minus BA equals V in times A, so equals minus, so I'm reversing the signs to make it plus. So V out to V in equals A over 1 plus BA. And the significant, and you've seen it before, otherwise you're in the wrong class today. Now, the significance of this is that if A is large enough, if the gain is large enough, the only thing which determines the transfer function is the feedback. Because if A wants to go to infinity, BA is much bigger than 1, so A over BA, A cancels out, and you get 1 over B. So the transfer function of the whole system is 1 over B for very large gains, which is very good, because it means if the gain changes, it doesn't matter. So if the plant changes, something changes, doesn't matter. The only thing that matters is this element, which is a sampling element, which takes a feedback, okay? And at large units of gain, it's 1 over B. Now, it also shows you the danger of feedback, briefly. If BA becomes negative, and let's say BA becomes minus 1, okay? Which can happen because the phase can change. At high frequencies there is a phase shift. We'll talk more about it today. So this can start becoming negative. If this reaches 1, you'll get A over 1 plus minus 1, so it's infinity. Okay? So if you have an open loop system which is just a gain of A, it can never run to infinity. If you have an amplifier with a gain of A, you put in a signal, you get a big signal. If the gain is very big, you get a very big signal, but you couldn't have a situation where it will run away and go to infinity or start oscillating. But if you have a feedback system, and there is phase shift here, that BA can become negative, because if the phase shift is too big, it reverses the phase of the feedback, and again we'll discuss it a bit later. So this can become 0, the thing can run to infinity. So normally, if you do a transfer function, and again I'm sure you've seen it before, if this is overall, or this is V out divided by V in over frequency, an open loop amplifier typically looks like this. At higher frequencies, the gain goes down. If you close the loop, you will get a constant gain, which equals 1 over B, as shown by here. And at the end, it will just roll down. But if something goes wrong, if there is too much phase shift and so on, you'll get something strange like this, and to the point where it wants to go to infinity. Is that clear? Good. Okay. If something here is not 100% clear, you're missing a lot of background, and you should catch up on it. So James Watt in 1788, much before electronics, even before electricity, understood that concept, that you can do feedback. The plant is a steam engine. The B, the feedback, is the spring and the weight, which cancel each other. And basically, you control the valve, which drives the steam engine. Okay, and a bit after him, a fellow by the name of Nasmyth. Okay, so Watt you know how to spell, because same as a unit, Watt. This was 1788, but around 1840, a fellow by the name of Nasmyth thought this feedback idea would be a very good idea to control big machines by hand, like you do today with some hand-guided robotics, right? And the machine he wanted to control was a steam hammer, because in those days everything was done by forging and casting, still done today actually, most big stuff. And I'll show you what a steam hammer looks, because I don't think you've ever seen one. And then I'll show you how it works with feedback. So first to find, okay, so this is what a steam hammer looks like, and it's a huge thing. Look at the size of the people behind it. Okay, you take a billet of red hot steel, okay, and you can't stay too close to it, and you hammer it until you shape it into the right shape. You may not be aware of it, but all big machinery is still done like this today. If you look at the shaft of a wind turbine, okay, if you look at big gears, and anything big today is still done exactly like this, and the machine looks exactly like this. Okay, so the trick is how to control it if you want to forge like an octagon or square, and you have to forge it very accurately. So the trick was some kind of a servo, and I'll show you now a quick video to show you the servo. So, oops, sorry. So this is a much smaller steam hammer. If you watch, it's a bad video, if you watch the right hand of the operator, the big hammer follows exactly the right hand motion. See, when you, not the left hand is something else, but if you look at the right hand, see, when he moves the right hand, the big hammer exactly follows. And matter of fact, when Nasmyth was demonstrating the steam hammer, and this I'm talking about the big one in the previous picture, so when Nasmyth was demonstrating it, he would take an egg and put it in a wine glass, okay? So in this steam hammer, to demonstrate the quality of the servo, he put inside an egg in a wine glass, and he showed that he can crack just the top of the egg with this huge hammer. And then they took out the egg and put in a 100-ton billet, and he could hammer it. So this was done because the big hammer was servoed to the handle. So if you move this handle a millimeter, the big hammer moved a millimeter, and it had no backlash because it was done with a steam servo. So any tiny movement on the handle made the big hammer follow with perfect precision. Okay, so this is another example of a servo around 1840, and from this we jump to modern servos, because modern servos are all electronic. So then we jump to the first guy who thought about electronic feedback. And if you didn't know about Watt and Nasmyth, you probably wouldn't know about this fellow, because strangely enough he was completely forgotten, but he invented one of the most important things in basically mechatronics, the electronic servo. His name was Harold Black. Harold Black, and in 1927 he worked for Bell Labs, and Bell Labs were into the telecom and long distance telephone. But now when you do long distance telephone, you have to put in repeaters. Repeaters are amplifiers you have to put every couple of miles into the line. So if you wanted a telephone line which goes across the US, every few miles you have to put in an amplifier. And you have big problems. Problem number one, the total gain was very unstable. Because, say, if you patched in at some place, or if the amplifiers drifted, since you had like 100 amplifiers in series, the total result was very unstable. If each amplifier changed 10% with time or temperature, you could have hundreds of percent change at the end. And the second problem was a bit of distortion, because if each amplifier distorts the signal a bit, at the end you get more and more distorted. So Harold Black was thinking, how can you make amplifiers which are very low distortion and never change characteristics? So he thought, using the same idea as James Watt used for steam, he thought of using it for electronics. You'll put an amplifier here with a very high gain, and you'll put a feedback, and if the gain is high enough, the total gain of the system will be 1 over B. It wouldn't depend on the amplifier. It would just depend on the feedback, and the feedback is just a resistor. If this is electronic, the feedback is just a resistor, so the feedback will be very stable. Okay? Remember, in those days, amplifiers were with vacuum tubes. That's before transistors, and actually it was expensive to build a high-gain amplifier, because each vacuum tube only gave you like a gain of 20, let's say. So Harold Black went to his bosses at Bell Labs and said, you know, I suggest to do that, then the amplifiers will be stable and so on. And his bosses said, it's a very bad idea. He said, you are saying instead of making an amplifier with a gain of 100, you are saying we should make an amplifier with a gain of 10,000 and then throw away 99% of the gain. Because that's what you do in a sense. If this is a graph, the open loop gain is very high, but when you put feedback in, you throw most of this gain away. But you throw it away to make the system independent of the gain, right? So his boss said it's a very bad idea, we can't understand why you want to throw away 99% of the gain. And he argued with them, and like so many historical breakthroughs, it wasn't appreciated right away. But then he built the system and showed them, and what was so good about Black is that he understood not just the fact that it will be stable in gain, he understood all the other subtleties, what feedback buys you, and many students who graduate control today, they still don't understand what he understood in that paper. The paper is available on the internet. If you Google Harold Black, you can see it, but I want to explain some of the things he understood and their importance. So let me show you Black's paper, which, as I said, it was reprinted many times and available on the internet. Okay, so this is Black's paper. Okay, and let me talk a little bit about the subtleties he understood. So the first thing he understood, besides stable gain, that a system like this will have much lower distortion than an amplifier without feedback. Okay? So now, if you paid attention in previous courses, you would know why a feedback system which have much lower distortion. Could somebody explain it? Okay. How many here took any control course in the past? Oh, not that many actually, about half. Okay, so the ones who took some control course in the past, okay, you have a better chance of answering. Why would that system greatly reduce distortion? So think of it what the system does, and any servo system compares the input is what you want to get, to the feedback, which is a sample of what the output is, and tries to make them the same. Okay? That's all what the servo does. It constantly looks at the output, tries to make it the same as the input. So what happens if the output has distortion? You put in a sine wave, and the output, let's say, ends up some kind of a distorted sine wave. Okay? So if you do that, what will the system see? It will see here a, say, smaller version of the output, because it samples the output. We'll compare it to the input. So what will it do? It will try to force the output to look like the input. Because if the system takes the difference between this and tries to cancel out the difference. Okay? So if the output is distorted, and this is not distorted, if you subtract them, you get some error signal. What you get at this point is the error signal. Okay? But if there is distortion on the output, it will show up as an error signal because the output doesn't look like the input. And if there is an error signal, it will force the amplifier to cancel it. Is that clear? Okay. But you should have known that if you took control courses, so maybe you should refresh a bit, like control theory, because otherwise the rest of the stuff I'll talk about you would have a hard time understanding. So what I suggest is kind of for this weekend, do a 1-hour refresher on control theory. Okay? So Black understood that and pointed out that not only would it fix the gain when you connect a bunch of amplifiers in series, but it will reduce the distortion a lot. And that's a very important thing. Think of audio amplifiers. Everybody is worried about distortion in audio amplifiers. But if you put feedback inside, they have less and less distortion. It will reduce the distortion by basically the amount proportional to the excess gain. So if you have an amplifier which has a gain of 100 and you close the loop and give it a gain of 50, there is not that much excess gain to fight distortion and so on. But if you have an amplifier with a gain of 1,000,000 and you use it at a gain of 100, the amplifier has a lot of gain to detect any small difference between these two and fight it. Okay? For example, if you look at an op-amp, the open loop gain of an op-amp is typically 1,000,000 to 100,000,000. If you look at the spec, it says 80 dB, sometimes it's in dB, but you know how to convert, right? So a gain of 10 is 20 dB, and it's a logarithmic unit. So anyway, if you look at most op-amps, they have 120 dB, okay, which is 1 to 1,000,000 voltage gain. But when you use them, you usually need a gain of 10, a gain of 100. So when you look at most op-amps, you are only using it here, and you are left with a huge gain inside to fight the errors. Is that clear, that whole thing? Good. So Black understood that and said, if you do that and throw away most of the gain, in other words, if you make A go to infinity, like be very high, not only will we get a constant output 1/B, but the distortion will go down a lot. Roughly go down by how much excess gain you have in the system. Okay? But Black understood something else, which is very critical. In amplifiers, you like to have usually a high input impedance in order not to load anything, but you like to have a very low output impedance. And why do you like to have low output impedance in an amplifier? Think of it, any amplifier you used. Is it better to have a high output impedance or a low output impedance? Think of a power supply, which is also a servo system.
More efficiency?
Pardon?
More efficiency?
It is somewhat related, but that's not the main reason. See, what would happen if an amplifier or power supply will have a high output impedance? Exactly. As soon as you load it, the voltage will drop. Makes sense, right? Because if you have a box, a black box, which is an amplifier, and the amplifier has a high output impedance, it looks like an amplifier with a resistor in series. And that resistor is Z out, the output impedance. So as soon as you load it, you get a voltage divider, the voltage drops. So an amplifier, the voltage will drop, a power supply voltage drop. So you want to have as low an output impedance as possible, so the voltage is stable. Okay? So how does the negative feedback affect the output impedance? So then you start thinking, let's say if you load this. What happens if you load this and the voltage starts dropping? What will the servo do?
You get an error signal?
Pardon?
Your error will...
Your error will go up because this voltage is compared to the reference. If the voltage starts dropping, the servo will fight you, will start to pull it back up. So if the gain was infinite, and most servos are designed with a very high gain, if the gain was really infinite, the output impedance will appear to be 0 because when you load it, it doesn't drop up to a point where it can't keep up with the current. So if you draw the voltage, say let's call this current and this is voltage. So if you have a regular amplifier or regular power supply, the more current you draw, the more the voltage drops. Think of a battery, right? But if you have feedback inside, you draw more and more current, but the voltage doesn't drop until it no longer can supply enough current, and then it collapses. Okay? So the tilting graph is like something with no feedback. The flat one is something with feedback, like a regulated power supply. Is that clear? Okay. Again, if anything here is not 100% clear, you really lack the background for this course, and you wouldn't be able to understand anything in this course. So you have to catch up on your own. Okay? Good. So Black understood that A, the gain will be constant, B, the distortion will go down, C, the output impedance will appear 0 or near 0, and if you're talking about a more slower responding plant, it has one other advantage, which in this case, in case of an amplifier, doesn't apply, because an amplifier has very low inertia. As soon as you connect the signal, it comes out amplified. But plants which have inertia, the feedback gives you one more advantage, and this is much faster response time, and I'll explain why. Let's say you have an oven without feedback. So if you run the oven at very high power, it will get too hot. So let's say you have a heater, this is time, and this is temperature. So if the oven wants to reach a certain temperature, this is the temperature you want to reach. Like think of a kiln to make pottery or any kind of an oven, baking oven in the kitchen. You want a certain temperature, okay? And if you didn't have feedback, if you gave it too much power, the temperature will keep increasing way beyond what you want. So you have to give it less power so the temperature will stabilize where you want. Okay? And that's how all open loop ovens work. Okay, you just give them just enough power so the temperature stabilizes. Say the older version of soldering irons. They just had enough power to get a certain temperature and it stabilized. Okay? But it takes a long time. And if you give it too much power, it will get too hot. But if it has feedback, it can ramp up at very high power until it reaches a temperature and then start cutting down the power. So if it has feedback, it can stabilize very fast and not overshoot. And if it doesn't have feedback, it will take a long time to stabilize, otherwise it will get too hot. This is no feedback. So basically the feedback for a slow plant makes it behave much faster. Is that completely clear? Good. Okay, so this guy Black understood all these things, wrote this classic paper, strangely enough was totally forgotten, to the point that last year there was a book published about Bell Labs. The book is called The Invention Factory. And it was quite popular last year. And the book lists all the great things which came out of Bell Labs, like the transistor, information theory, but it doesn't mention Black even in one word in the whole book. So he was forgotten to that degree. Okay, good. So now, but there was a clever student at Stanford University who did a master's degree in controls, and he needed to stabilize an oscillator, because at those days, when you built an oscillator, as soon as you change the frequency, the amplitude changed. Because oscillators in those days were just a LC circuit, coil and capacitor, but since the gain changed with frequency, when you change the frequency, the amplitude changed, and that was very annoying. So people wanted an oscillator that you can change the frequency, but the output stays constant, just like all oscillators today. So there's a student who did a master's thesis, and let me show you that. And he came up with a feedback idea. So he said, this is, again, vacuum tube days. The year was 1939, okay? And what he did there are two triode amplifiers, which act like MOSFETs, basically. If you think of today's chips, these act like MOSFETs. But he put a lamp, it says R19 lamp, and there is it says there negative feedback in series with one of the lamps, okay? And the way this works, that an incandescent lamp changes resistance a lot as it glows brighter and brighter. Because it glows brighter, the filament gets hotter, and if the metal gets hot, the resistance goes up. You know that, right? For example, if you take a light bulb, a regular incandescent light bulb, and it says on it 120 volt, 120 watt, okay? And you measure it with an ohm meter. How many ohms will it read? So 1 amp. The light bulb says 120 volt, 120 watt, so it means it draws 1 amp. So 1 amp at 120 volt, if you measure it with an ohm meter, how much would it read? Okay, so you're saying 120 ohm. Any other opinions? Did you ever try to measure a light bulb with an ohm meter? So, okay, if you try, the bulb which says on it 120 watt, which means 1 amp, which should read 120 ohms, reads like 30 ohms. Because it's only 120 ohms when it's hot, when it glows. But when it's cold, it's much, much less, because it heats up to 2000 degrees, right? So the change is huge in resistance. So if you take a light bulb and put it in series, it becomes something towards a constant current supply or a current regulator, because if the current wants to go up, the light bulb starts getting hotter. As it gets hotter, the resistance goes up and limits the current. So one of the earliest type of current regulators was just a light bulb. It's still one of the best way to charge batteries, rechargeable batteries. You put them in series with a light bulb, so at the beginning the voltage of the battery is low, the current is high, and as the battery gets full, the light bulb gets dimmer and keeps the charging current a bit constant. Anyway, so this student at Stanford put in this light bulb as negative feedback. So if the output of the oscillator wants to go up, the current goes up, the light bulb heats up, and because it heats up, it doesn't allow the current to go up. So that's negative feedback, simple negative feedback. So the company he started, based on this idea, had revenues last year of $120 billion. So what's the name of the student and what's the company? Come on, guys, here. I see you are weak on history of technology. Okay, here, I'll show you the product. Maybe this will give you a hint. That's the product. The circuit you saw before is a circuit diagram of this product. And that was the beginning of a company with today's revenues $120 billion. One of the biggest companies in the world. Microsoft? They didn't start in '39, and yes? Hewlett-Packard. Good. Well, it says Hewlett-Packard actually on the slide. You see it says HP. So the student was Bill Packard, and his master's thesis was a stabilized oscillator, And when he graduated, he went and built this together with Bill Hewlett, okay? And they started the company Hewlett-Packard, and their first product was an oscillator where the amplitude stays constant because it has feedback. It's like a servo system, basically. So you can see the capacitor. The thing in the middle, this bank of plates in the middle is a variable capacitor. So the way it worked, it had, you can see from the schematic how it worked. But basically, it was a RC oscillator, I think, because you know you can build an RC or an LC. I think that was an RC oscillator. Let me check. Yeah, it was an RC oscillator, and it had negative feedback to stabilize it. It was a sensation, and just a tidbit, the first big customer was Disney because they needed sound effects for the movie Fantasia. So they bought 7 of those oscillators. That was the first customer. Anyway, the rest, there is an HP virtual museum online, and you can see more pictures and the history of that. So this took control theory. So Black took control theory from mechanical systems to electronic systems, and people started using it. Everybody used it at the beginning. It was a huge advantage, like Bell Labs used it, and Hewlett-Packard used it. And basically, that's how it went on. And the next big step was in World War II, around 1942, where what's called today modern control theory was developed. And the reason why this control theory, sometimes referred to as PID control. You heard the term PID control, right? Yeah. So usually here in the feedback, you have proportional elements, and you can put derivatives or integrators, as you learned in the control courses. So in general, it's called PID control because you can use here proportional, integral, or derivative to match the job. But there is something called modern control theory, which uses all kinds of more sophisticated ways, not just the feedback. A lot of times it uses feed forward. You know the term feed forward? Yeah. So, and predictive servos and state variables and more and more complicated things. Today, servos today actually use machine learning techniques. They just try to anticipate and learn. So who is a fellow who took control theory from this, which was fully explained by Black, to the next level with all these learning ideas and feed forward, what's called modern control theory? Who did that? Pardon? No. He contributed a lot, Kalman Filters, but not, he didn't move control theory to the next level. Somebody else at MIT was professor at MIT. I think MIT. Norbert Wiener. Did you hear his name, Wiener? Okay. Norbert Wiener, and he did it in roughly 1940. And what was Wiener's motivation? Do you know the background? Why is a big interest in servo systems in 1940? So usually there's a reason why people work on a problem. Yes? Pardon? No. There, at the same time, there was also the Norden bomb site, which did use some of these elements for bomb targeting. There was a Sperry and Norden bomb sites, but that is not Wiener's work. But you're very close. Well, in a war, remember the war, you either shoot or bomb. So it wasn't bomb, it must be shooting. Right? So what did they want to shoot in World War II, which was so difficult and needed big servos? Aircraft, okay? Because what happens that at that time they already had radar. They could see the airplane with radar even at night, okay? But it's very tricky to automatically track an airplane. Especially if you don't see it at night, only the radar can see it, right? But even if you see it, it's difficult to track an airplane. First of all, because obviously if the airplane is flying and you aim the gun at the airplane, by the time the shell will reach the airplane will be somewhere else. So obviously you have to aim the shells ahead of the airplane so they will meet. But it's much more complicated than that, because there is crosswinds. So if the airplane goes this way and you aim the shell this way, they not necessarily meet, because any crosswind will cause like this. So first you have to estimate the crosswinds. But it's even more complicated than that, because anti-aircraft shells have a proximity fuse. What a proximity fuse is, it makes the shell explode even if it missed the airplane, because otherwise most of the shells will do no damage. So as it flies by the airplane and the shell senses it's moving away, it explodes. Okay? So the pilot sees he's being shot at, because the pilot sees shells blowing up in the air, and he's taking a evasive action. So not only you have crosswind and you have to go like this and guess where it will hit, but the pilot, when he sees the shells, does this. So it becomes a very complicated control theory, including some unpredictable components, because there is a human in the loop which tries to defeat you. So Wiener builds the first advanced control system which includes all these things, plus it has a model of the pilot's psychology. Because statistically, they looked what pilots did when they were shelled. And let's say 70% of the pilots did this way and 30% did this way. Okay? So when the pilot was shelled, the servo gave more weight to the chance that the pilot will do this and tracked in this direction. So basically, it was the first, what's called modern servo. It had an estimator for the errors and a predictor for what the pilot would do and a regular servo to track, and it was a complicated thing. And it was put in use. The work started in 1940, and 1944 was deployed very, very successfully. Hundreds of those anti-aircraft batteries were deployed and shot down many German planes, and mainly German planes and Japanese planes. It's quite amazing to take such a complex system in 2 years from concept to deployment. Okay, and that was the work of Wiener. So he wrote the classic book, which unfortunately is very heavily mathematical. It's not that readable. It's called something about the estimation of time series, but it's very mathematical. But he wrote a bunch of popular books, and he used the term cybernetics, which some of you may have heard, right? I don't think he invented the term, but he called this whole modern control cybernetics. And he wrote about half a dozen very popular books of all the uses of cybernetics, which are still interesting to read. But, okay, so that's a short history of control system. And from Wiener's time till today, there was really no new idea in control, but many improvements. Because this concept that you can make a sophisticated control system with machine learning and this and this and this, it becomes better and better as computing power gets better. But conceptually, what a control system can do and cannot do and so on, it didn't really change from Wiener. That was the last conceptual breakthrough in control, because what he included is already elements of machine learning. This learning the pilot's behavior and predicting and all this was already precursor of today's machine learning. I mean, this was all done with vacuum tube computers, right? So we couldn't do it to the same degree as today, but the ideas were there. Good. Any questions about history of control systems and servo systems? Good. Okay, so now we'll move to the next thing. We can turn off the projectors. Okay, this projectors off, projector system off, and we turn off the computer. Okay, good, and we don't need this. Good. So now Okay. There is actually one more name I should mention for completeness. I mentioned that the problem with this elegant concept is if there is phase shift and the signal here starts changing phase, and at some point the negative feedback becomes positive feedback. This will become unstable because this is connected as negative feedback. The feedback is connected to the minus. So if the signal is too big, because it comes in negative, it brings it back to being small. But if you would reverse it, okay, if you reverse the polarity or reverse it here, okay, it can do the opposite. If the signal becomes too big, it will come in and make it bigger. Let's say both are plus. This is minus plus, and this is a difference. Let's say if I have a colored chalk, very clearer. So let's say that somehow, because of phase shift, this becomes plus instead of minus. So this, instead of subtracting, it adds up to the input and becomes bigger. But once it becomes bigger, it becomes even bigger, and then adds again and starts growing as basically growing uncontrolled until it saturates or oscillates. Okay? So clearly, there is some relationship between the stability and the amount of phase shift you can tolerate and amount of gain you can tolerate. Because clearly, if the gain is less than 1, it can never oscillate. Because even if you reverse the polarity from minus to plus, so you get a signal, if the gain is less than 1, it comes out smaller than it came in. Once it comes out smaller, it's sent back again with plus, but comes out even smaller. So if your gain is 1/2, the signal ends up here half, comes back, ends up half again. So instead of growing uncontrolled, it shrinks uncontrolled. Okay? So clearly, for a system to oscillate, the gain of the plant, A, has to be more than 1. Is that clear to everybody? Good. Now, and if the gain is, let's say, more than 1, 2, 5, 10, if that phase shift is small, it wouldn't oscillate. Because if this has no phase shift at all, everything will be perfect. It will take the difference and control it perfectly. Now, if the phase shift is small, it's not going to make a big difference. Okay, it only starts becoming a problem as when the phase shift becomes so big that instead of taking the difference, it takes the sum. So at what phase shift will it be the sum instead of the difference? 180. But when does a difference become a sum? When you flip the sign. So if you have a sine wave, and you take the difference between this and this, in order for the difference to become the sum, this has to reverse completely, right? So it's 180. At 90, you get somewhere in between, sum and difference. But 180, if you have a difference and this switches 180, it's the same as changing the sign from plus to minus. Okay? So it starts becoming clear that for this to oscillate, two things have to happen. The phase shift has to be 180 degrees and the gain has to be more than 1. Now, if the phase shift is less than 180 degrees, let's say it's 170 degrees, it will still oscillate, but the gain has to be more than 1. Okay? Because it's not exactly the difference. Right? If the phase shift is like 90, it probably will never oscillate. But you can calculate that, because you can calculate the value of this, because this is a transfer function, and this transfer function produces a graph which I drew there. This is V out, V in, and again, if this was the open loop gain and everything was perfect, okay, the closed loop gain will look like this. Now, if the phase shift starts building up, this starts reversing polarity and cancelling the 1, and then it will start what's called peaking. The amplitude will start growing, And it always happens at this end. In other words, when it starts becoming unstable, it looks like this. And then if the phase shift goes even higher, then it starts oscillating. It goes to infinity. Now, can somebody explain why is the problem always occurring here at the end before it rolls off? Like it will never oscillate here in the middle. It will always oscillate here. So I'll give you a hint. When we talk about phase shift, what is the physical cause of phase shift? What causes phase shift? Delay. Very good. Okay, so several of you answered right. So delay causes phase shift. So now think about it, and now tell me, why would it always oscillate at the end? Yes. And
more signal through, so a delay makes it bigger.
Very good. Because the higher the frequency, the same delay makes a bigger phase shift. For example, if I have a sine wave and I have a delay of this much, this is delay. Okay? Make it more clear. Delay. So if I have this delay, the sine wave will look like this, and the phase shift will be, let's say, 30 degrees. Just to make up a number, 30 degrees. But if that sine wave is twice the frequency, the same delay, exactly the same delay, now will give you a bigger phase shift. Right? If the frequency of the sine wave doubles, the same delay now, let's say, gives me 60 degrees phase shift. And if the frequency of the sine wave goes up and up and up, at some point the same delay will give me 180 degrees phase shift. Right? If this delay equals to half a sine wave, so if I go to a sine wave like this, where this delay is half a sine wave, when I draw it with a delay, it will look like this. It'll have a 180 degree phase shift. Is that clear? So the same delay gives me a bigger and bigger phase shift. So at some frequency, the same fixed delay will actually reverse the phase completely. So the negative feedback will become positive. Is that clear, everybody? You better stop me if it's not clear, because you wouldn't be able to follow the rest. So, is that clear why the same delay, no matter how small, at some frequency will give a 180 degrees phase shift, and then the feedback will become positive and it will oscillate? Okay? So why doesn't it oscillate here? Because here the delay will be even a bigger phase shift.
Because then it starts going the other way. Once you pass 180 degrees, then you're going back towards zero.
True, but that's not the reason, because then it will oscillate maybe at some other point where it's again okay. No, it's a much simpler reason.
The system gets smaller with higher frequencies.
The system gets what?
The response gets smaller.
There is no gain, because here there is no gain left, because this is a gain curve. So at some point there's no gain, and we already established intuitively if the gain is less than 1, it cannot oscillate, because each loop it becomes smaller. So basically, if you take the wrong feedback, if you flip the feedback from negative to positive, and you put it into a system with a gain smaller than 1, it will look like this. It'll get smaller and smaller and smaller, because each time it goes through the loop, signal gets smaller. But if you flip the phase and you put it in a system where the gain is bigger than 1, it'll be the other way. It'll get bigger and bigger and bigger, because each time it goes through the loop, it gets bigger. So if the gain drops below 1, it doesn't matter what the phase shift is, it can't oscillate. So from this we can make some law that the threshold of oscillation in any system is when the gain is 1 and the feedback reverses the phase. In other words, the phase shift 180 degrees. So if G, which is gain, or the system gain, okay, if the gain is actually, in this case I called it A, so maybe we stick with A. So if A if A is greater or equal to 1 and 180-degree shift, this is a threshold of oscillation. So anything above that, if A is bigger than 180-degree phase shift, or even if A is much bigger than 1 and even this is less than 180 degrees, it can start oscillating. Okay? But this is a threshold condition of oscillation. Certainly nothing can oscillate if gain is smaller than 1. Okay, so this is basically a very good rule to remember, that this is a threshold of oscillation in servo systems. And who is a clever guy who came up with this rule? It's called stability criteria, and named after another clever guy who worked at Bell Labs, who came out with that in 1936, roughly. So, you know the name, but you just don't connect him to the formula. Nyquist. Have you heard the Nyquist criteria? So at least some of you did. Okay, so this rule, the guy who formalized it was Nyquist from Bell Labs, and this is still named after him, Nyquist stability criteria, and there are whole mathematics to go with it. When you look at poles and zeros of a system, how can you figure out if it's completely stable, conditionally stable? And this is just a highly simplified version of his work, but what's important is this criteria. That's the most important thing. But he actually provided the tools to draw graphs, which are called Nyquist maps, which graphically show you the stability, or mathematically show stability. Okay, so basically when you have an amplifier and you connect it with feedback, and you test it with a scope and oscillator, if the graph comes out like this, you don't worry at all about stability, because you know there is no tendency to oscillate. But if you take this amplifier and you plot it and it looks like this, then you start getting a bit worried, because you say somewhere there's a phase shift developing which can destabilize it. Because if it's this, if something changes, it can become this and oscillate. So this thing in telecom is called peaking, from the word peak, and it gives you an idea how close you are to problems in a servo system. This concept is true for any system, robotics, servo, telecom. Say you, for example, you made a robot which moves the arm, and you want to make sure this robot wouldn't suddenly become unstable. So what you do is you can drive it with a sine wave. You tell the robot to do this, and then you go faster and faster and faster and faster, and you measure the amplitude as a function of speed, and you plot it. And if towards the end it gets like this, you know there is some instability, and there is kind of a fight between the gain dying out and the phase shift increasing, but it's dangerous. Okay, so you can estimate from this how close you are to trouble. So you can do this with an op-amp by simply sweeping the frequency, looking at the op-amp output. You can do that with a robot, you can do that with a kiln, you can do that with a whole industrial plant, which is controlled by feedback. So this principle is universal. Typically you see these graphs relating to simple op-amps, right? But this graph or this concept is true for any feedback system in the world. Could be hydraulic, could be very complicated, you know. Even could be a complex modern system with predictors and machine learning and everything. If you run it faster and faster, and if you see this, you know that it may be unstable and you worry about it. Where does the delay come from? So the thing which kills the stability of servo systems is a delay. The delay in the sensing, or delay can happen inside here too. Either delay here, somewhere there's delay, usually in the plant itself, because the sensor can be made fast. So the delay causes phase shift. The phase shift increases with frequency. So there's two things fighting each other. The phase shift gets worse and worse with frequency, but the gain drops. So if the gain is still high enough when the phase shift is near 180, it will oscillate. And usually you have to design the system that the gain will die before there is enough phase shift to be unstable. And that's what you do in op-amps when you sometimes add a capacitor. So when you design with op-amps, say this is an op-amp, and you have, let's say, inverting op-amp, and you test it and you get this problem. It's a bit unstable. Sometimes op-amps become unstable because of capacitive loading, like a cable capacitance. So when it becomes unstable, the typical solution is this. What this does, it makes the open loop go down faster, right? Because it increases the negative feedback for high frequencies. So because of that, it cannot oscillate because it runs out of gain. Okay? Now, there is a second source of trouble in servo systems, which is more rare but hard to fight. Sometimes you have a resonance. Let's say, especially in mechanical servos. So let's say you build a robot or you build a table which moves under servo, but the structure itself has a resonance at some frequency. And this is very common because every mechanical structure has natural frequencies, resonances. You know that from mechanical engineering, right? So why is the resonance so bad? So say if you take the open loop system, in some systems, especially mechanical, the open loop, instead of looking like this is F and this is A, because of resonances, you can get a system which looks like this, has some mechanical resonance. Okay? So why is that so bad? Pardon? Yes, but why is it so bad if you close the loop? This was open loop. Now you want to close the loop to a servo system. So why do you care? If there is a resonance, why do you care? You are closing the loop. It will hold the gain constant. But when you try it, it doesn't work.
The errors will get higher at that point.
Pardon?
The errors between the signal and the reference and the output will get higher at this point.
But let's say you have plenty of gain. Let's say you have plenty of open loop gain. So the errors get higher, but the servo should suppress them, just like it suppresses distortion. But in reality, if you have a resonance and you close the loop, it doesn't behave like this. It actually goes crazy where the resonance was. Let's take a very specific example. You have a cantilever. You want to flex it with an electromagnet. So you have a cantilever, you put electromagnet, the current bends the cantilever. But every cantilever has a resonance because it's like a tuning fork. Okay? So let's say you take a cantilever which resonates at 10 hertz, but you try to move it with a coil from 0 to 100 hertz. So at 10 hertz it has a resonance, but the servo should take care of it, should force it. But when you try it, it doesn't work. The servo goes crazy at 10 hertz. Why is that?
Because it critically is stable.
Pardon? Yeah, but why? What is the underlying reason why suddenly the servo stops working when it hits a resonance?
Because your feedback also goes way up.
Yes, the signal goes up, the feedback is constant, but the error signal is big but this is supposed to cancel it, right? Let's say at the resonance frequency this goes up, but this is supposed to bring you back a big error signal, and the big error signal should suppress the resonance.
But it's not instantaneous.
Pardon?
But it's not instantaneous.
You're getting closer, but because that's what a servo does. If there's an error, it suppresses it. If there's a big error, there's a big current trying to suppress it. But you try it, it doesn't work. So this question is really a question of mechanical engineering, to understand what happens in a resonance.
Starts becoming nonlinear, probably.
No, let's say it's completely linear. If it's non-linear, for sure you have trouble, because this thing assumes linearity. But a resonance like a cantilever is completely linear. So what else happens in a resonance? Okay, so is a resonance a first order system, a second order system? Second, good. And what happens to the phase in a second order system? Because in a second order system you draw amplitude and you draw phase. So what happens to the phase in a second order system? That's a mathematical question. It has nothing to do with servo. Okay? The phase changes 180 degrees. If you look at the differential equation of second order system and you draw amplitude and phase, any resonance implies a phase shift. It could be much higher than that, but at least to be a second order system, the phase changes 180 degrees. But this whole servo doesn't work if the phase changes 180 degrees. As a matter of fact, by that point, there may already a phase shift. There may be a phase shift even without the resonance. So it doesn't even have to change 180 degrees. It only has to change by enough that the natural phase shift plus the resonance will push it 180 degrees. But the resonance alone will push the phase shift 180 degrees just by the second order equation. Because resonance, the driving force and the position are out of phase. And at resonance, they wildly reverse phase. Just look at the graphs of a second order system. So any resonance implies wild phase shifts. And the wild phase shifts will reverse the feedback polarity and instead of negative become positive. And that's a big problem in servo systems. And if the resonance can be very steep, the phase shift can be huge, much more than 180 degrees. Now, you probably know from differential equations that the slope of the plot, this is referred to normally as a Bode plot, because usually it's plotted in log units. It's log frequency versus log. Are you familiar with the term Bode plot? Yeah. So it's log units. So in a Bode plot, when you have a certain slope, it corresponds to a certain phase shift. So for example, 6 dB per octave on a Bode plot corresponds to 90-degree phase shift. 12 dB per octave corresponds to 180-degree phase shift. That's straight from the differential equation. It's nothing to do with servo. So if you have a very steep resonance of many, many dBs per octave, it implies huge phase shifts. So if this is like 100 dB per octave, it's thousands of degrees phase shift. So even the slightest resonance, not just a steep one, but even a tiny resonance like this, can give you immediately 180-degree phase shift, and the thing will be unstable. So the two big problems in servo systems is delays, which cause phase shift. And delays usually come from the plant, not from the sensing. And we'll talk about it later. And if you have any resonances, they cause huge phase shifts and delays. Okay? But the biggest problem is that if you have something where the output is not in phase with the input, okay, that's the phase shift. So when things resonate, if you take a cantilever and you drive it by hand and you measure the position, near resonance, the tip position doesn't follow your hand position. So actually it could be an antiphase. Okay? So because that implies a huge phase shift. It means you can never stabilize it. Okay. Is that clear? Okay. So what I suggest that most of you, if not all of you, do a quick refresher this weekend on servo. I know you took the courses, I know you learned it, but I also can see your retention isn't that great. Okay, so, I mean, I've been teaching the same course many years, and so I can see every year the retention is worse. Okay, it's not that you didn't understand it at one time. Your retention is that all the things I asked you today you should have known. Okay, so you should please go back to your control theory 101 and go over again what is phase shift, what is gain, what is Nyquist criteria, what is closed loop, open loop, delay, all the stuff I mentioned today, because if you don't do that, you wouldn't be able to follow the rest of the lectures. Okay, thank you.